Hi, I'm Lucy, and I will be sharing our work on a decentralized and encrypted national gun registry. In the United States, while we've been dealing with this pandemic, the epidemic of gun violence has worsened. Particularly in the past month of April, this has captured more of our national attention as we've witnessed what feels like one high-profile tragic shooting after another. Just since March 16th, when 8 individuals were killed in a racist attack against Asian American women in Atlanta, there have been at least 50 mass shootings. We've also seen an uptick in gun violence of every kind and increasing support for gun control measures, as well as recent legislative focus on addressing gun violence. Today, I'm going to talk about one legislative proposal addressing gun violence and our work in assessing its feasibility. But I wanted to say up top that we're not claiming that technology will magically solve anything or that any one policy can fix gun violence. We recognize that this is underpinned by much deeper issues, for example, those related to racial justice, healthcare, or economic disparities. The focus of this talk is on a specific legislative proposal drafted by Senator Wyden's office for a decentralized and voluntary national gun registry that explicitly guarantees data privacy and local control over data. This was also envisioned as part of broader gun control laws and to help support a background check system, as well as assist with the gun tracing process. Currently, if an unidentified firearm is found and more information is needed, the process involves physically searching through file cabinets and boxes full of forms, as shown in these images. And this on average takes 4 to 7 business days, of which only 65% of traces can be answered. And this inefficiency is intentional. Under the Firearm Owner Protection Act of 1968, we actually can't have a centralized national gun registry, which this decentralized proposal would not violate. But as a whole, we currently do not have an efficient means for tracking the sale and ownership of firearms. When Senator Wyden's office approached us with this idea, they had a specific question they wanted to ask. They were curious whether a decentralized encrypted national gun registry could be possible at the scale of the United States, and if the legislative requirements they had conceived could actually translate to concrete cryptographic protections. Our role as cryptographers was to answer these specific questions about this specific piece of legislation. Gun violence is an extremely complex issue with different avenues for making change, and this includes addressing the underlying issues that lead to gun violence or passing statewide reform. Therefore, we recognize that federal gun reform is only one piece of this puzzle and one that has been prone to stagnation. So when we first began this project, our expectation was not necessarily that the system would be instantiated. Our hope is that our work helps to foster a dialogue about what trade-offs are possible in realizing a national gun registry for when and if there is a right time to have this conversation. So to begin, I'm going to discuss at a high level what a system like this would look like. A key property is that all of the data is encrypted and locally managed. For a single state, such as California, each county would designate a local official who holds a key. This is used to encrypt license and registration data for the county, which is stored in that county's own encrypted database. Each state operates a server which stores all of the encrypted local databases for the counties. Its only role is to store data and to maintain its availability. All of the counties then send their databases to the state server. And if we abstract this out, we have the California state server, which holds data for some number of its counties. And around the country for each participating state, there would be a state server holding local data for all of its counties as well. And each state will have varying numbers of local officials, with new ones choosing to opt in or opt out at any point. Together, this composes a gun registry that is a system of decentralized, locally managed, encrypted databases that can be queried by authorized users around the country. Now that I've talked about the high-level goals, I will address the system requirements based on the draft legislation. 1, each county designates a local official who is responsible for an encryption key. 2, the encryption key is required to view, query, update, and encrypt county data. 3, authorized users are permitted to query the system for registration and licensing data. And this might be a detective or local official from another state who wants to perform traces, or a distributor who might want to see if an individual has a valid license before purchasing a gun. 4, attempts at collecting large amounts of information are prohibited, and this will be regulated at the county level based on factors that they have determined. 5, authorized users must be able to make queries even if the designated local official's key is offline for some pre-specified amount of time. So this is necessary since different regions vary in levels of internet connectivity, and if there were to be unstable internet connection, data from the county should still be accessible. I won't be covering this today, but the details are in our paper. 6, once a key has been offline beyond that pre-specified time period, data pertaining to the county should be completely inaccessible. And this just allows counties to opt out of the system without affecting the ability of other counties to participate. To realize these system requirements, we leverage the following cryptographic building blocks: secure two-party computation, structured encryption, and secret sharing. Secure two-party computation, or 2PC, allows for the computation of a function over private inputs from two different parties while producing a public output. Structured encryption allows a user to encrypt a data structure, store it in an untrusted environment, and perform private search queries on top of that data. And this is done by using the encryption key to generate tokens that are specific to a query. These tokens are sent to the server, who then returns the response without knowing what the query was. Secret sharing allows a party to split some secret into what are called shares. These shares can be used to recombine the original secret based on some threshold, but the shares on their own do not reveal any information about the actual secret itself, not even partial information. There's precedent for national gun registries, but none with the same set of security and privacy guarantees outlined here. Canada operated a national gun registry, and a key criticism was that the data was centralized. New Zealand passed legislation in 2019 for the creation of a registry, and individual states in the US also have their own versions of registries. There are also some superficial similarities with federated encrypted databases, such as Conclave and SMSQL. These are two systems that also leverage secure computation for private query execution over databases, but in their systems, the query is evaluated on the union of data held by all data owners, whereas here, once a database is identified, the query only needs to be evaluated over a single data owner's data. I will now describe our protocol, but wanted to add that it's one of many ways to fulfill the requirements of the legislation. The system, however, received positive feedback from members of Senator Wyden's team. In the interest of time, I will be focusing on the querying process. The full protocol is described in the paper. So panning back out to this global view, we have all of the state servers who hold encrypted local databases. An authorized user with a query may already know which county to make their query to in the use case of a distributor looking for licensing data, but a user trying to perform a trace would not know which county a gun originated from. And to prevent against this worst case scenario of having to query every database in all 50 states, we introduce an encrypted global directory. This encrypted global directory contains key value pairs of serial numbers and county IDs. We want to store this information in a centrally accessible place, but we do not necessarily trust a server to have access to this information. Therefore, we encrypt it using a structured encryption scheme. We introduce two custodians whose role is to hold shares of an encryption key for the encrypted global directory and to be online to service requests. Let's say a user has a request for county ID corresponding to a serial number. The user first secret shares their serial number into two shares, one for each custodian. The custodians then participate in a 2PC for generating a query token for the user to be able to retrieve the county ID. The custodians begin by inputting shares the serial number and key into the 2PC. As the first step, the serial number and key are reconstructed. They then serve as input for the encrypted global directory's token generation function, and this comes from the structured encryption scheme. This produces a decryption key and token. The key and token are secret shared and then outputted back to the custodians. The custodians then pass the decryption key shares to the user who reconstructs the key. The custodians also pass the token shares to the server. The server, now that it has the token, can return the ciphertext containing the county ID. And using their decryption key, the user can now decrypt and obtain the county ID. So going back to this view, the user now knows which county to query in order to receive the full record they're looking for. At this stage, the user can now make a direct query to a specific encrypted local database. So just to take a look at these encrypted local databases, each record in a database will contain some basic information about a gun owner and their firearm, and this might include the owner's licensing ID and additional information on the gun. A user can then make different types of Boolean queries on this data, such as a simple query with just one single keyword, or more complex destructive or conjunctive queries. These are some examples of queries, but based on a county's rate limiting practices, these queries might be invalid depending on the volume of records returned. So to begin the querying process, the user has some query queue and the local official has a key. These two parties must participate in a 2PC so that the user's query and the local official's key are both kept private. In the 2PC, the query and key serve as inputs for a token generation algorithm that comes from the encrypted local database's structured encryption scheme. This then produces a query token. The 2PC outputs the token to the user, who forwards it to the state server, and the state server then returns an encrypted result corresponding to the query. In order to decrypt the ciphertext, these two parties need to participate in another 2PC. The inputs here are the ciphertext and the key. First, a decryption key is generated using the record ID of the ciphertext and the official's key. This decryption key is then used to decrypt the ciphertext, which is returned to the user. The user now has the record in plain text, and this concludes the querying process. I wanted to point out that the local official does learn the number of ciphertexts inputted into the 2PC, but nothing about the contents. They can then conduct rate limiting by refusing to decrypt if the number of ciphertexts is too high. There can also be additional checks that are added into either of the 2PCs for more sophisticated rate limiting. Moving on to security. The legislation implicitly defined trust relationships that we extracted and formalized into a threat model. We only consider security against semi-honest adversaries and construct security in the ideal real-world paradigm, where we make comparisons between the execution of our protocol in the real world and the execution of an ideal gun registry functionality. We tolerate the following corruptions, which we categorize as external or internal. For external, we tolerate the corruption of the server and one of the custodians. For internal, at most one local official. A full proof is in the extended version of this paper on ePrint. An important piece of this work was to evaluate if this was even possible at the scale of the United States. We therefore implemented the protocol end to end and then ran experiments based on the estimate of the number of guns of the United States. We also did a basic cost analysis to confirm the financial feasibility of running a system like this, and that's also in the paper. I wanted to highlight a few metrics, starting with the encrypted global directory. Here we have the number of serial number county ID pairs that are already in the encrypted global directory on the x-axis. This shows that the time it takes to add a single pair into the directory is independent of the number of items already stored. We were interested in looking at what happens when there are 400 million pairs in the global directory, since that's the number of guns estimated to be in the United States, according to the Small Arms Survey. And it would take 377 milliseconds to add a pair with 400 million pairs already in the directory. The time it takes to find a county ID is also independent of the number of pairs in the directory. And on average, it takes 247 milliseconds to find a county ID with 400 million pairs in the encrypted global directory. And moving on to the encrypted local databases, it would take less than 4 minutes to add 100,000 records. As for query performance, the query time depends on how complex a query is and the number of records returned as a result of the query. This chart shows that it takes less than a minute to respond to a query that returns 100 records. A query returning this many records likely would not be valid, but we included this metric as a demonstration of the performance of the system. As shown, 2PC decryption time encompassed almost all of the query time. Lastly, for storage, it would only require 110 gigabytes to store 400 million serial number to county ID pairs in the encrypted global directory. Using the set of keywords previously shown, which included basic information about a gun owner and a firearm, it would take 1.7 gigabytes to store a local database with 100,000 records. Before I conclude, I wanted to acknowledge that introducing a protocol designed specifically for data collection by law enforcement does have the potential for abuse. In the case of driver license and license plate databases, they've been used beyond the intention of their collection for targeted deportations by ICE and facial recognition algorithms by the FBI. We kept this in mind when thinking about how the data stored could be misused. While we can't control how this protocol would be deployed if it were to ever be deployed, we strongly advocate for policies and regulations that limit personal data collection by law enforcement and full transparency on access control. New developments in cryptography as a whole can enhance privacy, but the use of privacy-enhancing technologies can also be used as cover to request access to more data. Therefore, we believe that policies and laws that specifically outline and communicate clearly to the public what kind of data can and cannot be collected before a system is built and deployed would help deter potential for abuse. To conclude, we designed, implemented, and evaluated an end-to-end encrypted national gun registry explicitly using draft legislation. This work shows that it is possible and practical to run a system like this at scale. And in working with Senator Wyden's office, we hope that this collaboration will encourage more of its kind between policymakers and technologists. We'd like to also thank their office for sharing this draft legislation and for providing valuable feedback. And thank you all for listening to this talk.